Hi everybody. Starting with the addition formula for sine and cosine, there are a few other identities that we can derive, and some of them turn out to be pretty important both in applications and when you do eventually get to calculus class. So let's have a look. So here's the addition formula for cosine. Cosine alpha plus beta equals cosine alpha times cosine beta minus sine alpha times sine beta. And if you see what this looks like, if alpha and beta both happen to be just the same thing, theta, now usually they aren't, but if you declare they are, then this identity looks like cosine of, well, if alpha and beta are both equal to theta, then alpha plus beta is theta plus theta, and that's 2 theta. And then the right-hand side turns into cosine theta times, so this alpha is really theta, times cosine beta, but beta is also theta, and so here we're getting cosine theta times cosine theta, so that's cosine squared theta minus sine alpha, which is, remember alpha is just theta, times sine beta, but beta is also theta, so that's sine squared theta. So this identity gets called the double angle identity for cosine because it tells you what cosine of twice an angle is in terms of sine and cosine of the original angle. And this identity actually comes in 3 flavors. So here's one with both cosine and sine. But I hope those squareds make you think, hey, if we wanted to, we could use the Pythagorean identities to shuffle this around a little bit. And indeed you can. So let's see how that works. Let's start by changing this sine squared. Now remember, the Pythagorean identity for sine and cosine, we can rearrange it to figure out that sine squared theta is 1 minus cosine squared theta. And that means this sine squared theta we can replace with 1 minus cosine squared theta. And then when you simplify this, keep track of all the minus signs, you get 2 cosine squared theta minus 1. Of course, backing up a little bit to this first version that we got, instead of replacing the sines with cosines, we could have replaced the cosines with sines. And that would give us, let's see, cosine squared theta is 1 minus sine squared theta. And then minus the sine squared theta that was there to begin with. And when you simplify this, you get 1 minus 2 sine squared theta. So here we get sort of 3 versions, 3 flavors of the addition of the double angle formula for cosine. There's this first one with both cosine and sine in it. The second flavor has only cosine in it. And the third flavor has only sine in it. All right, well, let's see what happens when we start with sine instead of cosine. So here's the addition formula for sine. And remember, we are imagining that theta is alpha and beta. This turns into sine alpha plus beta, that's 2 theta, equals, let's see, sine alpha is really theta times cosine of beta, but beta is really theta, plus cosine of alpha, but alpha is really theta, and sine of beta, but beta is really theta. And now if you look at these 2 terms, they're both actually the same, so this is 2 sine theta cosine theta. So there's an addition formula, or I'm sorry, a double angle formula for sine. It turns out really there's only one flavor of the double angle formula for sine, unlike for cosine. So let's see a couple examples of how we can use these new identities. Got one all queued up over here. So first example, if we have some angle theta and we know that cosine of theta is 1/3, and also that theta is between minus pi over 2 and 0. So this means that theta is in the, that's going to be the fourth quadrant. Then let's find sine of 2 theta and cosine of 2 theta. Let's start with sine of 2 theta. Well, this, I hope that, given what we just saw, I hope this makes you think, hey, let's use the double angle identity for sine. And remember, the double angle identity for sine is sine 2 theta is 2 times sine theta times cosine theta. Okay, and we know cosine theta already, so that's good. But sine theta, we don't know sine theta yet. We're going to have to figure out sine theta. So over in the margin here, let's figure out sine theta. And I guess we could maybe draw a most important diagram. Something like this. And we noted that our angle is in the fourth quadrant, so like this. So here's our right triangle. It's not a very good right triangle. And the top side of this right triangle is a third, because that's cosine, and we're in a unit circle. The hypotenuse of this right triangle is 1, because we're in a unit circle. And so the right-hand side of this right triangle is going to be the square root of 1 minus 1/3 squared. So that's the square root of, let's see, 1/3 squared is a ninth, so 1 minus a ninth is 8 over 9. And simplifying the root, that is 2 root 2 over 3. And in this picture, in this most important diagram, sine is this y-coordinate. So, oh, I have made a horrible mistake. I need a plus or a minus here because the Pythagorean theorem can't tell you whether you get the plus or the minus sign when you take this square root. So it's plus or minus 2 root 2 over 3. And since we're in the fourth quadrant, we're going to take this minus sign and discard the positive possibility. So it's negative 2 root 2 over 3. And, of course, in this unit circle, the y-coordinate is actually sine. So negative 2 root 2 over 3 is sine of theta. All right, so now we do know sine of theta. We can put everything we know into the double angle identity here. We get 2 times sine of theta, which we now know is 2 root 2 over 3, along with that minus sign that I keep trying to forget, times cosine of theta, that's a third. And so altogether we have negative 4 root 2 over 9, it looks like. All right, so there's sine of 2 theta. Now let's find cosine of 2 theta. For cosine of 2 theta, remember we have 3 flavors of double angle identity to choose from. Let me scroll over so we can have another look at those. They're the 3 with the yellow arrows. So we can choose either to use cosine and sine, just cosine, or just sine. And if you look at our values of sine and cosine, sine is negative 2 root 2 over 3, and cosine is just a third. A third is such a nice number to work with. I think it would be best to only use cosine if we can get away with it. So let's use the flavor of double angle formula for cosine that only uses cosine. And remember, that is 2 times cosine squared theta minus 1. And now we know what cosine is, or what cosine theta is. It's a third. So now we have 2 times 1/3 squared minus 1. So 1/3 squared is a ninth, so 2 over 9 minus 1. And that is going to be, looks like negative 7 over 9. All right, and there we go. We have sine of 2 theta and cosine of 2 theta. Notice that cosine of 2 theta is negative. That means for this unknown angle theta, twice that angle actually pushes us over into the third quadrant because both sine and cosine are negative. All right, let's look at one other example of how we can use the double angle formulas. Let's use them to demonstrate this identity, that secant of 2 theta is secant squared theta over 2 minus secant squared theta. All right. Now it's kind of tempting to start with the right-hand side because it looks more complicated. But actually, having this 2 inside of secant on the left-hand side, that actually makes the left-hand side a lot more complicated. So let's start with the left-hand side. Also, having that 2 on the left-hand side gives you a really good idea of what to start with. Use a double angle formula. Okay, so secant is 1 over cosine. We don't have a double angle formula for secant yet, and so we'd better just switch to cosine. So 1 over cosine 2 theta. And now that we have cosine 2 theta, we can use the double angle formula for cosine. Which form of the double angle formula? Well, right, remember we have 3 flavors to choose from. And if you look at our target, our goal for this identity, our goal only has secants in it. And secant is related only to cosine, so it seems like introducing sine into this whole thing is not necessary. So let's just stick to the flavor of the double angle formula for cosine that only has cosines in it. And that is 2 cosine squared theta minus 1. All right, so where to go from here? It's a little tricky to say. It's not totally obvious. But let's look at where we're headed again. You see this 2 here in our goal. It looks like maybe that is the 2 that's showing up next to cosine squared theta here. It's just there's cosine squared theta in the way. So we'd really like to cancel this cosine squared theta. And to do that, we could multiply this denominator by 1 over cosine squared theta. But if we do that to the denominator, we also have to multiply the numerator by 1 over cosine squared theta. Let's see what this does. So in the numerator, we have 1 over cosine squared theta. And then in the denominator, we have 2 cosine squared theta over cosine squared theta minus 1 times 1 over cosine squared theta, which is just 1 over cosine squared theta. And now, well, there are cosines all over the place, and sometimes they cancel, and of course sometimes they turn into secants. So 1 over cosine squared theta in the numerator, that's secant squared theta. And in the denominator, 2 times cosine squared theta over cosine squared theta. The cosines all cancel, and we just get 2 minus, and 1 over cosine squared theta is secant squared theta. And that's what we wanted. So now we've demonstrated that this double angle formula for cosine is actually, for secant is actually true. Fortunately, it turns out that really only the double angle formula for sine and cosine, and sometimes tangent, are useful. The double angle formulas for the others, secant, cosecant, and cotangent, almost never get used. So don't worry about remembering them. But do get used to how the other double angle formulas for sine and cosine work, and also have a look at the textbook to see the double angle formula for tangent. It comes from pretty much the same place. You take the addition formula for tangent and just plug in theta for both alpha and beta. If you have any questions, please let me know.